Okay, let's start then. Welcome everybody to the fourth day of the short course. I'm going to talk today about decision making under uncertainty due to renewables. And just to brief introduce myself, I am Maria Vrakopoulou, and I'm an assistant professor at the University of Melbourne at the Department of Electrical and Electronics Engineering. And in general, my focus is in the integration process of renewable energy sources in power systems. I'm gonna talk today about 4 different things. I will give some short introduction on the block 1 about the challenges that are related to the renewable energy integration, and specifically challenges that are related to variability and uncertainty. I will give you some overview of how the system is responding and why we do care about that when we are going to model later on the formulations of OPF, of co-optimization of energy and reserves, and etc. So later on in block 2, I'm going to start giving you some details on how to formulate a stochastic OPF problem. And specifically, I will discuss differences between robust optimization and chance-constrained optimization. Then the solution methodology there that I will describe for chance-constrained problems, it will be on the scenario optimization. And this is something that gives us the freedom to actually get solutions that have probabilistic guarantees. And it has a lot of kind of benefits around that. So at the third block, I'm going to continue on the same topic, but I will focus more on less assumptions regarding the OPF. I will talk about AEC constraints and how to satisfy them through different formulations in a stochastic manner. So this involves, in the end, the solutions with non-convex scenarios of optimization, and that are recent results that are really very strong as well, that can be applied to generally non-convex problems. At the fourth block today, I'm going to show you how to optimize energy and reserve within this framework that I will have described, and also more specifically go through reserves and energy that are coming from demand response, and specifically for thermostatically controlled loads. And I'll give you a specific formulation that one could deal with this kind of demand response in order to provide reserves and energy. And I will also discuss at the end some control policies and how you can really generalize control policies to get better and in an optimal sense results. Control policy is something that I will describe later. It appears everywhere, wherever I am applying stochastic methods in the OPF problems. But let's start. So the first block today is on renewable energy integration challenges. For sure, Nad already described a lot of things regarding the integration of DER, specifically PV in distribution systems. I'm going to touch something that is related with uncertainty. But before that, I would like to go through this kind of graph that I borrowed from a report from AEMO, the Australian Energy Market Operator, that shows how the penetration of solar and wind is going to be in a few years. So if we focus a little bit to understand what this shows, if you focus on the gray dots, you see on each dot, it's a half-hour instance of solar and wind penetration versus underlying demand. So it's a point that you are having this kind of instance in actual measurements that exist for 2019, and you add all these points together to have this gray cloud here. You may observe that you may have some you may observe you have points up here that are with high demand. You have points down here that are with low demand. And you do have points on this side that are more medium demand. And then when you see on the bottom, the axis, the solar and wind penetration, actually it is coming as a percentage of the underlying demand. So you see at this point over there, at the top of the underlying demand, then you do have more integration, actual value of solar and wind penetration. You have, for example, 25% if you are around here of the 35 gigawatts. That could be something like sunny days in the summer. You have a lot of sun. It is very warm. You have a lot of conditioning. That's why you have a lot of load over here. Whereas on the bottom, you may observe all these instances that could be from low demand seasons. Maybe some kind, these points over here would be from spring that you have low demand, but you have a lot of sun as well. Again, the percentage, it's a lot compared to the underlying demand. That could be a sunny day, for example. You observe we do have, for every 30 minutes that you do the measurement, you do have a lot of different points. So in total, you have a very big variability on what the values could be over here for 2019. If you observe what is going on in the red and the orange dot cloud is forecast clouds that AIMO is doing in order to see where it goes, where the penetration goes. And you see the orange that would be maybe quite optimistic, goes up to 100% of the underlying demand. So we are going to have a lot of solar and wind coming into the system, and that is something that we need to take care of because there might be issues with regards to the operation of the system. And before going to discuss more about the uncertainty and the variability that may appear due to the renewable energy sources, I would like to go to some basics, go through some basics in order to understand what does it mean when, for example, one value of the PV is changing to another value. What do we need to do? Why we care about that so much? So the power system in general is an interconnection system of synchronous generators, loads, and other assets. But the synchronous generators are those that are really creating this system frequency that should be maintained in a specific point, the synchronous frequency, in order to have a balanced system, and also to actually in the end work in a safe way. So basically the way it comes is the opposite. So if the system is balanced, then the frequency stays steady. If the system is imbalanced with respect to generation and load, then the frequency starts to move. For example, if I may write over here, I will just write in a very abstracted way how you can see that the frequency of the system, this could be the frequency of the system that is quite coupled with the frequency of each generator, that each synchronous generator that we have in the system. But why I'm writing that is because I would like to show that the mechanical power is the power that actually is generated by the generators, the synchronous generators, and then we do have the electric power that is consumed by the lines and that are driving to the loads, to the PV power somewhere, maybe at some other point, some asynchronous generators as well. So the thing is that in general, before having asynchronous generators, what we had is that the generation was actually changing just from this side, and it was going up or down depending on how much, for example, generated power we wanted to put in the system. If we keep the load constant and we increase this, that means that the frequency is going to increase. If we keep the load constant and we decrease the mechanical power, then this is going to decrease as well. The reality now comes that uncertainty comes more on this side. So this is what is fluctuates depending on, for example, what happens with the demand, what happens with the other single generators that fluctuate as well, and that creates the frequency deviations. In the ideal case, this P is equal to Pm, and the frequency then will be constant. However, if we go to the case that we do have the demand that varies, the wind power that varies as well, the PV power, and also some unexpected contingencies, it could happen that at any point within the day, we could have, or within the hour or the next minute, we could have an imbalance with respect to what the generators are scheduled to produce and what the network is asking to consume. So this is something that in the end, the power system is operating and is fixing what is going on with the mechanical power with different control schemes. And I'll explain a little bit what is going on with the frequency control schemes as it is done in Europe. And this is something that shows one kind of example that is actually taken from Swiss Grid, a transmission system operator in Switzerland. And this is actually something that shows the different levels of frequency control that we have. These numbers, okay, are taken from a few years ago. This could change in the future, or they can become smaller depending on what operation its TSO is doing. So here we do have different numbers than that in Australia. So just going through that, because I like the schematic and it's nice to explain the different operations. This kind of plot is showing the frequency here with respect to time. And you see that the nominal frequency, for example, is 50 Hertz, and it deviates a little bit. There is a point, it deviates anyway, because we do have always this kind of deviations in demand, on the demand side. And at some point over here in time, there is an outage. We didn't expect that. The scheduled generators were not really the ones that they didn't expect to have such a thing. And that's why the frequency dropped over here. So the generated power was not on at this level. So since we had this imbalance, and this means that we had a more generation suddenly than, we had more load suddenly than generation. So if you see this kind of analogy of P mechanical minus PE, suddenly part of that was lost. So this got smaller, and that's why the frequency started going down, right? There is the rest of the generators, so one of these guys disappeared, but the rest of the generators and the system has different levels of control in order to bring the frequency back to the nominal, around the nominal value. So the three levels of control could be described as the primary frequency control or the governor control. The second one is the secondary frequency control or the EGC, automatic generation control. The second is a tertiary frequency control or dispatch, redispatch, that different TSOs call it differently. The important thing to notice is that the primary and the secondary over here are automatic control loops, whereas the redispatch in most places happen manually, depending on what has happened in the system. Recently, different TSOs are starting doing more automatic updates of doing redispatch every 5 minutes, and so on. But here, this example shows the redispersion that is happening after 15 minutes, for example, of based on an event. So this is something that, as we see, there is a loss of generation. We have the drop of the frequency, and then we see this kind of increase of frequency going back there. This is because of the primary frequency control, that every generator that participates in that compensates a little bit of this loss. So for example, if you have the delta P to P for a specific generator, the change that is going to happen, it's really related to a drop and the frequency that is observed. So the measurements are locally, but they are very strongly coupled all together, with a steady state point to be the same. So it measures the frequency locally, each generator. It has its droop, and as you see, it is in the way that if the frequency is getting low, so negative, this is the deviation from the nominal, then the primary control is going to react to give more power to certain generators. So this is something that happens locally to each generator everywhere, based on the response that they see in the frequency. After that, what happens is that it's not exactly after that, these things happen simultaneously, but with a different time scale. So with a different time scale, secondary frequency control is running. This is something that, this is a control that is really operating for each control area. And each country usually has one control area or more. For example, I think Germany has 4 of them, but here France has one control area that is gonna now adjust the generators that participate in this secondary frequency control to compensate this kind of error and bring the frequency back to 0. This is a type of control that is PI, proportional integer control. It is happening in a centralized manner because there are measurements around, so a few measurements of frequency around the control area. They also measure the tie line power from the control area to other control areas, because with the HUC they try also to control the tie line power exchange. But in this specific case here, with this kind of frequency deviation, the aim of the action of the secondary frequency control would be the fact that there is a loss internally of this generator. And then other generators here are going to react in order to compensate this loss. All right, this is a continuous loop as of measurements around 4 seconds. Every 4 seconds you see what is the state and you get the feedback. And then the time scales is that, for example, it could be running in a way that within this 15 minutes after the disturbance, you're going to be having your steady state point of the secondary frequency control. So then when the system is really in a normal state with respect to the frequency, the operators, they do the tertiary frequency control. That could be participating generators from different also control areas, and the main goal is to do an economic dispatch then based on the new situation, because they had lost this guy over here. So all this description I'm doing here started because of the loss of the generator, but exactly the same thing can happen if, for example, suddenly we have a decrease of generated power because just the big cloud is coming through a distribution system on top of the distribution network, and we don't have any more the PV power. And we have scheduled the rest of the system to be operating with respect to a sunny day. So everything is working and is committed to work based on a sunny day. Suddenly you have the clouds, so you are going to have something like a loss of generation. And this is something that could be, what I'm saying, could be quantified a little bit better when we will go through later to understand what is the uncertainty and what is actually the way that we can take it into account in the optimization problems. So one thing that I would like to observe here is that this is a dynamic response of the frequency, but one could actually isolate the points, the steady state points that are related to its control, action, because it's on different time scales here in the specific example of in this TSO. So you could have a steady state points. If you want to analyze your system, you can calculate the steady state points, steady state in the sense that your system operates in this point for some time, for some minutes. And here again, your system operates at this with this profile, generation profile, for some minutes as well. So that means that in this sense, I'm talking about steady state points, but we are going to see a little bit later about that again. So here, I want to go back a little bit to the renewable energy sources, and I would like to draw two cases. The one would be something like that. Over time, you have the generation, and the other would be like that. And I would like to ask, for example, because I would like to make clear to people what we mean by variability and what we mean by uncertainty. And I would like to ask the audience whether, for example, they can see which of these two actual, let's say, measurements of the generation for 2 days that are sequential, for example, are more variable or, let's say, more uncertain. So maybe you can say what is 1 or 2 connected to more variable or more uncertain. How would you say that? I'm trying to see if I can really see any answer from your side. If you're right.
There is someone with the hands up. Do you want me to give them right to talk?
Excuse me?
There are some people putting their hands up, so we can allow them to talk if you want.
Oh, yeah, I haven't seen that. Oh, okay, they're up there. Yes, of course, we can allow for a quick question.
So are you going to do that or I do?
Oh, allowed to talk. Okay, I start with Dominic. Hi, Dominic.
Hi, Maria.
So you have a question regarding the question I just asked, or regarding all the material I have been discussing up to now?
I think I wanted to respond. You were asking if 1 or 2 it is variability or uncertainty.
Yeah,
I
please.
think 1 it is uncertainty, while 2 it is variability.
All right. Okay, thank you, Dominic. I will answer to that in a minute. Maybe we can allow somebody else as well. I will allow Chris.
Yeah, hi Maria, it's Chris Chandraj. I think number 2 displays less variability than number 1.
Mm-hmm.
More variability.
Yep. Okay. Oh, I have to mute you back. Sorry about that. Allowed to talk, and I will allow Jamie as well.
Yeah, I agree with the previous message.
I don't hear.
Hello? Oh.
Jamie, do you talk? Okay, I don't hear you. Okay, I will come back later if you want to talk about that, because I don't hear you. Maybe you can rhyme. So the question I made was a little bit tricky because it was not really to be answered for both variability and uncertainty, because I haven't discussed to you, for example, if I am talking about any kind of forecast. So uncertainty is related to being here, for example, looking ahead for some hours or whatever, thinking that something will happen, and suddenly, if you move towards the time, the actual time, you observe that something else is happening, right? So the uncertainty comes with respect to what we think, what we can predict. So this is coming, that this distance between what we forecast it to be and what is the actual value, if you go actually and measure what happened in the next day, for example, like here, then you see what is the forecast error. And this is actually what is what we discuss as uncertainty here. With respect to variability now, as somebody correct said, number 2 here is less variable than number 1. This is just respect to, we see actual signals, measurements, we see how they change. So for example, if something changes very much like that, we might know exactly that this will happen. So there is no uncertainty. It can be like, we know we have a perfect forecast, there is no uncertainty, but this is very highly variable. Because you see from one moment to the other, this is changing. But maybe this is, at this specific case, in my example, we know that. We are not surprised by that. But this means that we should have resources available to be able to compensate these kind of changes. Because as you remember, as we discussed before, the system needs to have balance of generation and demand in order to be able to maintain the frequency in a steady point. So as you see here, you might have points that you need very fast. So if the let's go to this main case. If you see here, the generation is dropping very fast in a very steep way. At that moment of the day, we should be able to have resources scheduled in order to increase the power, because we are losing generation. And this is under the assumption that the demand, for example, is constant here, just to create this toy example for you. Okay. And what we see if we go to the uncertainty example, is that if we have scheduled everything, for example, that and the system to operate at this point, and suddenly in real time you see that you operate at this point, that means that you should have you should be able to change the generation in a way, because it seems like you had more generation that you might need, so you can decrease the generation then to this point. Decreasing generation sometimes could be easier, or because some people also, if there is, oh, I'm sorry, I think I made a mistake here. So the actual value seems to be smaller than here. So that means that, oh yes, indeed, you have to be able to adapt to that. No, I didn't make a mistake, to adapt to that and decrease your generation. So, okay, the thing is that we are talking about generators that are going to respond to what's happening. We're talking about PV panels or renewable energy that are going to fluctuate. And let's assume that these guys over here that fluctuate is this. And these are the followers. So suddenly if we're talking about a constant demand, and you are really thinking that your generation will be like that from the photovoltaic or the wind, and suddenly goes down in reality, then you should have more generation from these guys to compensate that. This is what I want to say for the change you need to do due to the uncertainty, and the changes you need to do due to variability. All right. I hope that this is clear. In this next slide, I would like to show you just some examples of wind power forecast errors, because in order, we don't know the future, but we need to operate the system and schedule the system so as to, because we do have, for example, machines, synchronous machines that they do need a lead time. They have startup costs and constraints with ramming constraints. So we need to commit some, many times we need to do commitment earlier. And also, we cannot really do everything in real time in the end because of ramming constraints. So what we see here is that the one attempt of creating a forecast, and what the forecast error was around this kind of forecast. So these are data from two different systems, the one from ERCOT system and the other from Swedish system. And this is something that you may observe that the error here is percentage, and it can go up to 40%, where here you see 20%. It is not, you cannot say that it could be always symmetrical. It depends a lot on the nature of both actually the forecasting techniques you have, but also what is going on with the uncertain variables over there. So the wind in this specific case. So it's not typically Gaussian. For example, if you also operate the wind power plant more, for some reason, more closer to the upper limit, you will see something that many of the points will be at a saturation because the system will not produce even more power because of the curve of the wind production. So why I'm showing that is that all these errors over here that you see, all these instances are something that the system operator should be able to have resources to adapt for them. And the system operator will say, for example, this generator should have this kind of capability to produce more power in case, for example, you see that we have less than predicted wind power in the system. So the general thing here is that Gaussian approximation, many people are using that, are not something that are very accurate. And what I'm going to talk later in this seminar is formulations and actually a framework that really do not depend on any kind of distribution. We're going to use data, it will be data-based, and there is no assumption about what is going on with the distribution. We just need to have the data, and then we are going to be able to get solutions that have some guarantees. So this is an important thing because we get solutions that could generalize for the rest of the unseen scenarios, but with just taking some samples of the actual data we have or distribution of the data we have. We don't need to know it. So this fits very well with the reality that we don't really have a very specific distribution around the errors. So the forecast errors that are coming because of the renewables, they do create this generational load mismatch I was discussing. This is just again an example of, for example, having here different time slots, with the red to be the actual, like the average every 5 minutes, 15 minutes, 1 hour, whatever you want to think about it. And then we have the hourly forecast. I'm sorry, I have hourly here, not. So in the specific, it's hour, I have written hourly, it could be whatever. So the main point of this kind of graph is really to show that in whatever time interval you have predicted something, what it will come could be different. And for example, when you do have that, the fact that you have the hourly forecast to be over here, and suddenly the actual is over here, then you need to have resources to increase the generation. Or if, for example, the forecast is here and then you have more generation, you should be able to have the resource to decrease that in order to maintain the balance. So this kind of capability to increase and decrease the power is captured within the notion of reserve power. And this is, for example, if you see this kind of graph here, and assume that there is an upper limit on what we can, where we can be in this cylinder, and this is the bottom, we cannot go below. The operating point, for example, of a generator could be over here, but it has an upper limit, it has a lower limit. The operating point is a dispatch. For example, it can come based on an economic dispatch or something else based on the market. And then around that, there are some margins because of these physical constraints that the generator have. Within these margins now, there is the market for reserves, and different could say, okay, I'm going to do that much to go down, that much to go up. This is something that, based on how expensive each generator is, the allocation of the reserve can happen. There are different resources other than the generators that could offer reserve, and this is mainly based on the capability the resources have to increase and decrease the power consumption or generation. For example, we can have storage devices like batteries. We can have flexible loads. For example, you might be thinking that you can have a boiler and you can really control when it's going to consume power, because you just need to satisfy some temperature limits, and you can just defer it and say, okay, I will consume power in order to make it warmer a little bit later. So you can create different kind of patterns with flexible loads, depending on the needs they have, of course, and the flexibility they give you. Storage devices like batteries could be even more flexible, and generation is our traditional way of providing reserves to the system. Even though batteries, for example, are something that is already being used in many TSOs for primary frequency reserves, for example. So if I go back to the graph I told you about the frequency deviation and the different controls of the frequency, the capability that the generators have to move in order to bring the frequency back at the level of primary frequency control or at the level of secondary frequency control is related with the fact that they have been assigned to be able to offer this kind of reserve. So they have been paid for that. And this is something that it's a matter of the markets that are around this. And for example, for this kind of secondary frequency control could be related with the second frequency control reserve market. And this is something that you can incorporate in the end in your optimization and formulation in order to create a solution that makes sense from an economic point of view when you try as an operator to find the minimum cost reserve allocation from where to buy what is the best one, with the same time with the energy allocation. The energy allocation is something that will be related with the dispatch. So you can see from this kind of plot that if you decide to use this specific generator up here, because maybe it has cheap energy, then you see you cannot move it more later on if you need to use reserve from him, to allocate reserves to him, to this kind of generator. But if you put the dispatch somewhere like here, the option to go to give reserve is a lot higher until the maximum limit of this kind of generator. And this is a matter of optimization, where you put your dispatch so as to leave the space to optimize reserves as well. We will talk later at the last block of the seminar about that. All right. So, given the uncertainty and variability that appears, for example, in different inputs because of DRs, because of utilities, scaled wind plants and solar plants, you are going to see that this variability is something that transfers through the network because all the system is interconnected through the power flow equations, as you very well now know through the first 2 days of this course. And that means that if there are fluctuations over here, they could be translated fluctuations to a certain, for example, for this line, to fluctuations like that. And the thing is that in the past, this kind of integration of renewables was not that high. We didn't have a heavy loaded system. And this kind of small fluctuations here and there could be managed. And nobody was raising a flag for that. The thing is that now that we are getting to the system more closer to the limits and we have more penetration of RES, on the one hand, the RES could cover some of the demand that is also growing, but this could happen in a high risk due to the uncertainty. Here, for example, you may observe that in the case in the past, you might have this kind of variable thing and maybe uncertainty that will go around that in that way. But when we have more and more renewables, uncertainty around this could grow even more. So this is something showing an envelope of where this could go up and down if you take into account, let's say, distributions of the input, the generation input on different points of the network. And this is something that you can calculate easily just through straightforward power flow simulations. But the very critical question here is what we can do about that. Because suddenly we will see the system having violations on different limits, power flow limits, voltage limits, or even generation limits that they cannot really provide what they are asked for. So the question is what we can do apart from observing that these kinds of scenarios are coming actually. So this is something that goes to the decision making. And the decision making is something that is quite well structured in the way the system is working. There are different layers, hierarchical layers of how the system operates, from scheduling from a week ahead, for the week ahead or the day ahead or some hours ahead. a common thing about all these points that you try to make decisions about the future, and then you go closer, you make again decisions, you correct something or you add some more decisions. The common thing about all this stuff is that you do need to have forecast, to use forecast values of your uncertain variables. And you need to really see for what kind of setup you do care for in order to formulate the problem in the right way that gives you the answers you want to see. So the optimal decisions are something that are going to come given that there is a very well formulated problem, and answering the questions of depending on what kind of resources you want. For example, if you want to do something where the scheduling point is here and the deployment is 1 hour ahead, you have many different kind of way of controlling things, different resources that will be there to be optimized for. But if it is, for example, for the day ahead, again, you have more, for example, thermal type of generators that could be entering and be committed in a certain way. So the forecasting is very important because it plays a role even when you do the forecast for 24 hours ahead. It's important to make it better and better in order to commit the resources in a more accurate way, let's say. And of course, it is true as you go closer to the point of the deployment, the forecasting is getting better and better as you go closer to the point here. The thing though is, as I mentioned, is that you're not going to have all the resources available there because there might be related constraints with, for example, ramping constraints or others. So given the scheduling point that we are sitting here, we are going to see how to build decision making algorithms so as to relate to OPF always, in order to see what is going on at the deployment point and ensure that this is going to be secure. So I'm going to go a little bit more on the details of these 4 blocks that are important in order to build this decision-making algorithm that you need. As I just mentioned, we need a good forecast model. It's to create your forecast trajectory, but also we would like to know what are the potential forecast errors around that. So we need a distribution, really. We don't need only just the trajectory of the forecast. We care about what are the probabilities of deviating on that forecast, from that forecast, because this is creating what I mentioned before, the uncertainty kind of envelope that you might be facing the next day. For the forecast error, you might be able to, towards building the decision-making tools to use raw data. This is something that could be utilized the way I'm going to show you today, or if there are not enough raw data, you are able to, there are ways, this is something I will show you some graphs about that as well, is how to build error generators or scenario generators, meaning that, okay, you have some data, and how are you able to describe, let's say, this distribution of small data with more samples that maybe you will need to use if you are running a database optimization problem. And then there are other more conservative ways, because you could, for some reason, like to assume that the error is coming from an analytical described distribution, like Gaussian, like other kind of distributions. For the network response, this is the second big thing that I mentioned before, is we really have to know where we are really sitting at and what is the steady state point that we want to look at, because we're talking about creating a decision-making algorithm that is really depending on steady state points. For example, as I mentioned before, if we are talking about where the frequency settles after the AGC, after the secondary frequency control, we can consider that as a steady state point. And then the calculation we are going to do around that will be related to the reserve capacities that are seen for the AGC, the allocation that is done for the AGC, and there might be different other kind of resources that could be controlled fast in these time scales that we are talking about. Because if we're talking about forecast errors that can happen and we need to react in some minutes, that means that inside this optimization framework, we should take into account this kind of resources accordingly. In order to satisfy also the network constraints, because we don't just need to have balance in the system, we really need to not overload the system, the network assets, not to create any kind of security issue there. So in the optimization that in the decision-making algorithm, we need to take into account the network. And this is done by modeling the network as the real kind of equations that you saw earlier in this week, the ECOPF. You can have approximations like the DC approximation or other linearized cases. You may have convex relaxations to describe the system as, for example, the semi-definite programming or the SSP programming that are described in certain cases the network in an exact way. So you are having something like, let's say, a bit easier problem to solve because the initial network equations are non-linear specifically on convex. There are other algorithms as well to deal with network constraints that are based on heuristic iterative approaches. And I'll talk later today about one of them, that is the ACQP. That is also something that is used very widely in different utilities. So when we go and formulate the problem up to this point, now we have to care about what kind of stochastic techniques we are going to use. We might care about formulating the problem in a two states way. So we need to make some decisions now, but we want to wait to see what is going to happen in order to make the decision for that specific scenario, for example. This kind of formulations, though, do not create this closed loop with respect to what happens if another scenario is coming out there. And that is why it's better to close this loop by certain approaches so as to know what is going to happen if another scenario is outside of the one that you have used in the optimization. What is going to happen with the system security. And then we have different types of other stochastic techniques, like robust type of optimization or chance-constrained optimization. And I'll discuss a little bit more about them later. So I will be quite fast here in order to do our first very small break, because I have planned to be like talking for around 50 minutes and then have a 10-minute break, and then we move on like that. So after having said all this, it is here to highlight that the operator or whoever is to make decisions for a certain part of the network, whether it is distribution network, whether it's transmission network, or whatever part of the network it is, the decision to be made if you are able to control certain assets of the system is quite critical given the fact that we do have all these uncertainties in the system. And one way to think of including the uncertainty could be based on certain assumptions, and that is how things could go wrong in the end. Because as I mentioned before, this is something like not that much representative of what is happening with the errors in real time. You might try to use other kind of data to describe the uncertainty and the scenarios you may have, different trajectories over time to fit in your optimization problem like that. You might use the robust optimization. I'll describe a little bit more later about this. And the thing is that whatever you do and how big you assume or how even more data you use in here, this also reflects to how costly the operation is. So if you increase this kind of set of data to take into account, then the cost of operation increases as well. So there is some kind of trade-off over there that should be found, but it shouldn't be quantified without taking care of the security of the system. So one thing I would like to also say here is that you might do whatever you like with uncertainty and the data. And if, for example, the realization that is happening the next day, the next hours, or whatever, is the same with what you have considered in the optimization, then everything is fine. Everything is good. And your system will be secure, given that, of course, you have taken into account the security constraints into your decision-making algorithm. But the case, the problem is that, where is it? Here. The problem is that when something that is outside this set of scenarios, these different that you have taken into account, comes to get into the system, and then the solution, the decision you have made might not be appropriate for such realization. And then your system might be insecure and end up with different problems, overloadings, cascading events, blackouts in the worst case. So what I will do in the next seminar is to show how we can find a solution that would hold, meaning that we could have a secure operation of the system, even for unforeseen scenarios. This is a question and maybe a statement that can be very strong, but I will answer it in a way that the probabilities are coming into our game here, and nothing would be 100% sure, but still we will be able to quantify, for example, how much secure we will be in the next day. All right, so I will stop for a little break. I will see the questions as well. And Arthur, you can stop the video